Okay, last example here. Example 4. This one deals with a snowmobile going off of a cliff. A very small cliff, though. A 300 kg snowmobile is traveling at 16.0 meters per second when it comes to the edge of a small cliff. Since there's a deep, fluffy snowdrift 2.5 meters below the cliff, the driver doesn't slow down but goes right over the edge without changing speed. The question is, calculate the speed of the snowmobile when it lands in the snowdrift, assuming that he or she doesn't slow down because he or she knows it's a fluffy snowdrift. Okay, so there's the question. I apologize that it's so long there for you to copy out. Looking at the solution. So first of all, of course, I'll copy out a little picture here. So I have the snowmobile going at a certain velocity, which we're told, and then 2.5 meters below there's a snowdrift. So the before picture, snowmobile traveling. After, what's the speed when the snowmobile hits that snowdrift there? So technically, we're told the snowdrift is 2.5 meters below the snowmobile. Therefore, we could say that the snowmobile is 2.5 meters above, which will be used in that potential energy equation. So of course, as before, law of conservation of energy. All energy we have before must equal all energy after. So we have kinetic energy before, potential energy before. I have that. Kinetic energy after, potential energy after. Now, one of these is going to be 0 because when we hit the snowdrift after, the snowdrift is at a height of 0. So that whole potential energy after will be 0. And as you can see, I wrote that down over there. The rest of these, since I'm looking for velocity after, or speed after, when it hits that snowbank, that's the unknown right there. I'll have to figure out, I don't know the kinetic energy before, I don't know the potential energy, but I do know the variables m, v, g, and h. Now, once again here, you can see the m gets factored out, because it's common to both terms, so if you remember that from math class. MGHA is 0. And what I'm going to do is isolate for VA. So first of all, it's 1 times MVA squared over 2. So what I'm going to do first is multiply everything by 2, which will cancel that out. Multiply that by 2, and I end up with that. So 2M multiplied by 1/2 VB squared plus GHB. Of course, you can see the next thing here. It's M multiplied by VA squared, so divided by M. Okay? And look at that. Once again, masses cancel out. It's not dependent upon mass. So I have my final equation. I'm very close here. One final thing. Square root of each side to get rid of that. Square root. And I end up with this equation. So the m is gone, I have nothing on the denominator. Square root of VA squared is VA. Square root of 2 multiplied by this binomial inside the brackets, 1/2 times the speed, plus gravity multiplied by the height, 2.5. So I recommend you work this out in your calculator. So figuring this out, 16 multiplied by 16, because it's 16 squared. 1/2, I get 128. 9.8 multiplied by 2.5, 24.5. So add what's in the brackets first, then multiply by 2, then square root, and you should get 17.5 meters per second. Once again, try in your calculator to see if you can get that, because it's crucial that you be able to calculate that kind of question. And that's it. So that marks the end of the energy unit. So we looked at, to recap, kinetic energy, energy of motion, potential energy, energy due to condition in terms of gravity, combining them together to get mechanical energy, which is considering the sum of kinetic energy and potential energy in a situation. And then lastly, looking at the law of conservation of energy. The energy before a transformation is equal to the energy after a transformation.